Hello everyone and good afternoon. Today, on behalf of our lab, OU Community Residence School Research Lab, I am Himadri, along with my lab mate Rafia, will be presenting how optimization can help for improving the community's resilience using InCore. This is our current core lab team. This team is continuously supervised by our two amazing professors, Dr. Nicholson and Dr. Gonzalez. And Samuel and I, we are pursuing our PhD in Industrial and Systems Engineering. And Rafia is continuing his PhD in Data Science and Analytics. And William is a master student of our lab. And we are all working with different test beds for enhancing the community resilience. And this is our previous lab members, and I want to acknowledge them. I want to acknowledge Ivanji, Jorge, Del, and Tarun for their amazing support for developing the optimization model, and also for their contribution for integrating the optimization technique in InCore. This slide is an overview of how InCore is working and helping the community for enhancing their resilience. And the marked portion is where the extensive work are already done, and it's showing like us the current stage of the work, and all the damage stage and hazard modeling are done here. Then we move forward to our top section of this overview, which is I will say the prescriptive and predictive part of this model, which is help the community for the decision making regarding their retrofit of their buildings in different level, so that the community can be more resilient of the natural disaster, regardless of different type of natural disaster we are working on for different test bed. And the way our lab and we are working on, and this lab, we are mainly working on developing the optimization model, and by analyzing different retrofitting levels for different test beds. For that, we usually need to calculate different parameters and need to analyze them. And for this, and after that, we need to create our required input file for running that optimization model. And this is the area from where of the InCore we are taking help from there. This is like we are using the amazing power of InCore to calculate the different parameters we need for our optimization model. For example, we need the expected economic loss. We need expected the functionality which you're getting from here. And we also need the expected population dislocations, which we are all getting from the damage analysis and population dislocation analysis from the InCore. And then we are coming here in our decision-making stage where our optimization is working. And after running the optimization model, we will find our decision regarding the building retrofit. And this stage is like already integrated in InCore, and we are still working on developing or improving it more with Santiago. And after running all this, we will get our optimization result from InCore. So like we are working on making some like cool visualizations to make our result more understandable by the wide audience. And here we can see our optimization model, and here is our set of building groups. So this is quite a map of Joplin. So this is basically a user-defined group. It can be zip code, it can be block group, or anything which will be totally depending on the user who is going to use our optimization model. And then our model will require the set of building types. So this means different type of archetype or structural type. So this figure is taken from one of the paper of Dr. Vandeleen and Omer, and they worked on Lumberton, and they considered different type of building archetype. And me personally, in my work of Lumberton, I used this different type of archetype. And also we need different type of retrofitting decisions. For example, we can take a flood barrier for flooding. We can consider different type of roof structure for tornado. So it will be totally depending on the natural disaster we are considering. and also the user who is considering which test bed for which natural disaster. And then if I come for my decision variable, this is the main decision variable we are considered for, which consists of 3 different indices, I, J, K. And this I, which I mentioned, the set of building group, which is mostly user defined. This can be any parcel ID, any block ID, or even in the Puma label. Also, I'm considering in the second indices, the structure type, which can be the different type of building materials or different type of building structure, like education institute or hospital or residential buildings. And then in the next stage, we are considering different type of structure or design level, or we can consider specifically some mitigation measure to consider. And then our second decision variable is helping us to model our problem more efficiently. And then this is our parameter we are considering. So the first parameter will be the expected economic loss, which is directly connected with our one of the objective function, which is minimizing our total direct economic loss due to the building damage. And then I'm considering our second parameter, which is the expected population dislocation, which is connected with my another objective function, which is minimizing the population dislocation. And then I'm considering the expected building functionality. And after that, I'm considering to another major parameter of my model, which will work for like balancing my cost and benefit analysis for this optimization model. And this is an overview of how my data is required for running this model. So this is like the expected loss, where in the first indices, I'm considering the block ID for, if I say for the Joplin, and then I'm considering the structure type, and then I will need the retrofit level. And after considering all these indices, I will go for my expected economic loss. Similarly, the data will be same for expected functionality and expected population dislocation, but then we need another one, cost data, and this data will be given in our parameter data file, which Rafia will present. And also here we are showing our strategy cost data for implementing a mitigation strategy. And here's the data should look like, where the first one is the building group identifier, then the structure type, then I will say my current retrofit level where the building currently is in, and then I will say the future retrofit level from where to where I want to go. Like if the building is in 0 retrofit level, if I want to go for level 1, then what will be my strategy cost? So that will be like this. And this data is my cost related data of my optimization data set, which will be definitely presented by Rafia soon. And in my optimization model, I'm working with 3 different objective functions, as I mentioned: minimizing total expected direct economic loss, minimizing total expected population dislocation, and maximizing the building functionality. And I'm considering several constants of this model. We're working with budget level and also ensuring the building retrofit, number of buildings before and after retrofit. And I'm also considering the nature of my decision variable. So thank you so much. So in this stage, I will continue I will refer my presentation to Rafia, and she will be presenting our notebook for showing how our optimization is working there. Thank you so much.
Thank you, Himadri. Hi, everyone. I'm Rafia. I'm Rafia Bushra. I'm a PhD student in data science analytics studying at University of Oklahoma. And thank you so much for this opportunity to share our work. So starting from where Himadri left off, so this is, I'll be presenting our code for how we do the entire analysis for each of the objective function and determine their parameters using InCore. and then how we create the input files that will be required for doing the multi-objective optimization in NCORE, and then finally share the results and analysis. So we start by importing all the necessary libraries. These are our basic Python libraries that we need throughout the code. These are in core client, getting fragility curves. These ones are for visualization using PyNcore Viz. And finally, these are our analysis tools for doing building damage analysis for population dislocation and functionality. And then finally, we have the library that we need for the actual optimization. So we've divided this into 3 phases. The first one is creating the input data files that we need for optimization. We need 2 input data files, as Himadri discussed before, the cost-related data file or the parameter data file, which contains all the parameter or objective coefficients. And the second one is the strategy cost data file, which contains all the strategy cost for going from one level to another. So, so here we start by creating visualizing a hazard. So we're working with tornado in the Joplin testbed. So this is a visualization of the 2011 Joplin tornado, visualized using PyNcore Viz. Here, as we can see, the EF5, the highest magnitude of the tornado, was hit at the center. And then as we go outward, we have other magnitudes of tornado as well. And then, so this is just visualizing a tornado that already exists in NCORE. But we're going to apply the optimization to a simulated tornado, which is also EF5 magnitude. To do that, we first need to secure our building inventory file, which has to be a shape file. And we can, as with most of the data sets we use, we can either have our own local data set that we upload to NCORE and then use the data set ID like these, or we can use the ones that are already available. So for most of the data sets here in this notebook, we are using the ones that are already available for Joplin in NCORE. So we use the building inventory. And we map, again, using PyNcore Viz and NCORE. We map out the archetypes in Joplin. And as you can see, most of the archetypes are of archetype 1. So we have 28,000 buildings in total. And of that, 22,000 of it is archetype 1, which is all residential buildings. Next, we define the hazard type and the hazard ID. This is the hazard simulation, again, that's already available in NCORE. It's an EF5 tornado. And then we move on to creating the parameter or the parameter data file, which contains all the parameters. So we start using building inventory. So now this building inventory data is the same as the building inventory data we saw earlier. The difference being that this one is a shapefile and this one is a CSV file that we have to download and use locally so that we can manipulate it using libraries like pandas or other Python libraries. So we start making, so just by convention and tradition, I suppose, we call the parameter data file Qt data file. So we will be referring to the parameter data file as Qt data throughout the rest of the code. So we start out this data file as a subset of the building inventory, but by just taking the columns that we need from the building inventory. The GUID is the ID for every building. Block ID, archetype, and design level are the sets that Himadri discussed earlier. The sets that we need, the IJK or the ZSK. So the blocks are the level of granularity. So it's a group of building or it's a region that we have. And archetype is the type of building, like if it's a residential building, if it's a commercial or industrial building, a hospital, or like wood structure or things like that. So the type of building. Design level is the retrofit strategies, like some of the strategies that Himadri discussed, like using flood barriers or a different kind of roofing, things like that. So here we have 4 design levels, 0, 1, 2, and 3. Increasing levels means we have a higher level of functionality of the buildings and a higher strategy cost for those. And then appraisal value of a building, which we will need for calculating economic loss parameter later on, and also the year built of the building, which we will use to calculate building age, which we will eventually need for calculating the population dislocation parameter later on. And then we do some data cleaning in the next step, where the QT data needs to have certain features. It needs to have the 3 sets defined very well. They has to be named Z, S, and K, the block group, archetype, and design level. And it needs to have certain columns. So as we go through the entire analysis, we'll keep appending columns after every analysis to the QT data. So for now, we have the ZSK and some parameter and some quantities that we will need to calculate the parameters later on. So we start with building damage analysis because all 3 of our objective functions are dependent on this analysis, as it provides the damage state probabilities. For the building damage analysis, we need 2 input files. We need the building inventory data set in form of a shapefile that we defined earlier on, and also mapping, and also the fragility curve. So again, like any other data set, we can either define this ourselves and upload it to Encore and use that, or we can use something that's already available in Encore. And here we're using something that's already available. And then we set some parameters in our building damage client. So some of these parameters are the name of the output file, the type of hazard and the hazard simulation ID, and the number of CPUs that we want to use to run the model efficiently. And then we finally do run analysis to run the building damage analysis. So after that, we get the output. So all of this is defined in a function so that we can conveniently call this entire analysis module here. So here I call that function using a mapping ID that's for the retrofit level 0. And that's why I'm calling it damage level 0. And here the output gives us the damage states, the limit states, and hazard exposure for every single building. That is for every single GUID. The damage state probabilities are the only quantities that we need from this table. It's the probability of exceedance of a damage state. So a damage state 1, so the damage state 1 having a probability means the probability of exceeding the damage state 1 for that particular building. And using the damage state probabilities, we calculate the expected damage state probability, which is a weighted sum of the damage states. And we append that, and that the DS total is what we actually need from this analysis module. And finally, we match this table, the output table from damage analysis, to the QT data based on GUID, and drop all the columns we don't need and only add DS total to the QT data file. So once we have the DS total, we can move on to calculate all 3 of our objective function parameters. So the first one being population dislocation. We used in course population dislocation client to do this. It requires 3 input files: housing unit allocation, block group data, and value loss parameter. Again, using everything that's already available on InCore, though I have to say that housing unit allocation is usually not available for most testbeds, and people have to do the housing unit allocation analysis. The client is there on InCore, and you need to do the allocation analysis and get your own allocation file if it's not available. And once you have all your input files, you do load remote input dataset command to set all your input data files. We also need to use the damage results we got earlier from the damage analysis. And finally, we set all our desired parameters and run the analysis. And this gives us the population dislocation table here, which comes with 84 columns, but we only need a few from there. So we shortlist the columns that we want, which is, first of all, the sets Z, S, and K. And then we have our GUID, which is building IDs. We need our damage state probabilities. We need NumPrec, which is the expected number of people in a household. The PRDIS, which is probability of dislocation, and dislocated column, which is shown as true or false, as in whether a household was dislocated or not. So we do a little bit of data cleaning here again, where we convert the block ID to string. We take all our design level to 0. We assume that all our design level, all the buildings in Joplin start out at 0, but it's just a suggestion or just an assumption here. If we had enough information that some buildings are in other states, it's easy enough to make that change. And then the dislocated column, we convert from Boolean to 0 and 1. The DIJK column, we get that the DIJK parameter, we calculate by multiplying the number of people in the household times the probability of dislocation. That gives us the dislocation parameter. And our final shortlisted probability population dislocation table looks like this. And just like before, we merge this. Before that, we aggregate. We aggregate based on GUID. So here, one GUID or one block ID, one building can occur multiple times because it could appear in different blocks or archetypes. So we aggregate by GUID, and we apply the appropriate function to each of the columns. For DS total, we take a mean. For NumPrec, we take the max, because we don't want to average for the same building. We just want to take one value. We take the maximum value that we get for a single building. Same with dislocated, and yeah. And for the indices, it actually doesn't matter. We just take the min here, or the minimum, which is just a single value. So we aggregate based on GUID so that we have a unique GUID column over here. And then finally, we match this table with Qt data based on GUID and drop all the columns that we don't want. So now this is what the Qt data looks like. We have our ZSK, we have our first parameter, DIJK, and the quantities or the columns in between the appraisal value, the building age, and DS total, these stay in Qt data, but these are only for calculating the parameters. So next we calculate economic loss. We start by creating a B column. B is the number of buildings for a particular Z, S, and K combination. So we set this to 1 because we're going to aggregate and sum it over so that we can find the number of buildings in a combination. We group by Z, S, and K, and again, aggregate with the appropriate functions. So for the building column, number of building column, we sum. For appraisal value, we take the average. For building age, we take the median, because we don't want a very old building or a very new building to skew our building age. And then we have ds total, we take mean, and for dijk, we do a sum. So that gives us our first lijk, our second parameter, lijk. Oh, so lijk we calculate by multiplying ds total times ds total as in the expected damage state probability times the appraisal value of those buildings in a particular combination. That gives us lijk. We add that on to the qt data, and now we have two parameters in our parameter data file. Lastly, we do functionality. So for functionality, we're using an equation by John van der Linde that they're working to improve or enhance, and it's the equation that Himadri showed in his presentation. This is where we use the building age to create this RIJK parameter. This is again a tentative equation that we're using. Some other equation could be used here to create functionality. Following the equation that Himadri presented earlier, we calculate qt hat, which is functionality for functionality after time period t for buildings in a ZSK combination. So now we have lijk, dijk, and qt hat for every single ZSK combination possible, and that's what our qt data file or our parameter data file should look like. So now this entire process has been done for a single retrofit here. For assuming that every building was starting out at retrofit level 0, we did this. However, we need to do this again for retrofit level 1, 2, and 3. So that we can use that for optimized decision making. So here, what we did was we found more fragility curves for retrofit level 1 for all archetypes, and retrofit level 2 for all archetypes, and retrofit level 3 for all archetypes, and redid the building damage analysis and got the DS totals for all three retrofit levels for all archetypes. And after this, we have to run the entire process that I just described for retrofit level 1, 2, and 3. And that way we would get like something like QT data, something like this table 3 more times, like for each of the retrofit levels. And then we concatenate all 4 tables, and that gives us our final QT data. So once we have the final QT data, then we have finalized the first input table that we need for optimization. The second input data file we need is the strategy cost data file. And the strategy cost data file, what we're looking for is a table that shows us the strategy cost of jumping from one level to another for all combinations of Z and S, that is block ID and archetype. What we've done here is we've arbitrarily chosen some fractions of appraisal value that seems reasonable for jumping from one level to another. So here, by default and arbitrarily set, I'm using 10% of the appraisal value for jumping one level. So for going from 0 to 1 or 1 to 2, 15% of the appraisal value for jumping 2 levels, going from 0 to 2 or 1 to 3. And then 30% of the appraisal value for jumping 3 levels. So for going from 0 to 3. So I've created a function that can determine the strategy cost, and this returns a table, the strategy cost table, that shows the strategy cost of the strategy cost for each ZNS going from each K to K prime. And that's that concludes creating the input data files for optimization. Phase 2 is the multi-objective optimization itself.
Rafia, do you mind if I just interject really quickly? So I think one thing that is hopefully is coming through, and there's a lot of code going in there to create these parameters, but the way that this multi-objective optimization is designed is meant to start right here at phase 2, where, however, anyone wants to come up with their loss estimates, population dislocation estimates, functionality estimates, strategy cost estimates, whatever that happens to be, as long as it's in the form where it is an average across the sets within the set Z for each of the structural types that you're interested in, and you have the information associated with each of the retrofit levels or enhancement levels. So if you have that basic QT data, as roughly referred to it, and the associated strategy cost data, we would start here. So this is the idea. Everything else is meant to be user and expert defined. And then once we have that, we want this to be entirely modular. So we have input data that we don't necessarily need to know anything at all about where it came from or how we got there. As long as it's in this form, then we would conduct the multi-objective optimization. So if you happen to see some of the assumptions we made about appraisal cost percentages or anything like that, we are completely fine if somebody changes that or fixes that or whatever. We are trying to do something anecdotally to get this thing to start so we can demonstrate what this data file would look like. But ultimately, ideally, and Santiago is going to help us make sure this works, is if we have these two files, building related data, strategy cost data, then we can apply this multi-objective retrofit optimization for any of the test beds. So that's the goal. And then if you have any of your assumptions that are different about different types of things you want to optimize, as long as it's related, set up correctly in that building related data set, then, fingers crossed, ideally it should work. And so that's sort of the, design decision that we made a while back to try to keep things separate, input separate from the model, and then ultimately separate from the visualization as well. So go ahead, Rafia. Just wanted to throw that in there.
Okay, thank you, Dr. Nicholson. So phase 2 is the multi-objective optimization itself. And as Dr. Nicholson said, the first things we need are these two data that we just showed how to create. Once we have those data created, they have to be uploaded to InCore and using their dataset service client. And then we need the IDs from the files we uploaded there to use in the optimization code itself. Now, the multi-objective retrofit optimization client is already implemented in InCore and can be used. However, while running this, we ran into a few bugs and have been working with Santiago to correct those bugs or fix those issues. So we don't have the results of the optimization from the InCore run here, but we did run this locally using Gurobi, and we used the results from that local run to visualize the results in phase 3. So phase 3 is results analysis here, and we're using a local run of the optimization code, and this is the result file from that. And then here from the result file, we extract the economic loss, population dislocation, and functionality for all solutions. We are taking an average of economic loss and population dislocation so that it's per block group. And then we visualize the trade-off scenario between these three objectives in 2D using a color bar. So the first visualization is economic loss versus population dislocation, and the color bar on the right represents functionality. As we can see, economic loss and functionality here actually goes hand in hand as we have increasing economic loss toward the right. The functionality also decreases. So when we have higher economic loss, we have lower functionality. Though there is a trade-off between economic loss and population dislocation. And then we move on to produce similar kind of plots with alternating axes. So this one is economic loss versus functionality, and we see a similar trend between economic loss and functionality. And then finally, we have population dislocation versus functionality, with economic loss being on the color bar. As a future plan, one thing we're trying to implement is we're trying to make an interactive plot where users can select a plan. So for example, this plan right here, which has one of the lowest population dislocations and functionality. So the user should be able to choose any of these solutions interactively and be able to compare that to the baseline or compare it with another solution to study trade-offs and financial impacts and such. So yes, thank you for allowing me to share this work.